I originally created this tool, OpenVAT, because I thought it would be super powerful to be able to get geometry nodes animation in particular into Unity or Unreal. I love using geometry nodes for animation, and I think it's kind of an underutilized aspect of them, potentially because you can't really export it. So I have this little fish character here. I just rigged him with Rigify and did a little walk cycle. It's a little sloppy, but it is what it is. And I wanted to add a little bit extra to him. I didn't rig his tail, but I wanted to add a little bit with geometry nodes. So I just added this little sine wave position over time to his tail. And I could have done this in Bones, but I wanted to do this for Vertex Animation demo anyway to show you kind of the power of this. Most of the time this would be really hard to get into your game, say in Unity or in Unreal Engine or Godot. You can't export geometry nodes. Maybe you could export an Alembic file with the baked vertex animation, or USD is starting to include vertex animation, but it's still really heavy for game use. Vertex Animation Textures are a long-standing way to do this. So it is like how it sounds. A texture carries vertex position data. This top one was created with a method that I call a proxy offset method. And the one you see on the bottom was using a method called a world offset. And so I'm going to start scrubbing through the animation here. And you can see on the left in the texture, this is actually a second UV set. So this is UV2. And across the x-axis here, this represents all of the vertices in the entire mesh. And on the y-axis here, this represents time. More specifically, each pixel of this texture on the x-axis represents one vertex, and each pixel going down the y-axis represents one frame of time. I know this texture is 512 by 512, so that means there's 512 verts in each line, and you can see how it's broken up into multiple lines here. That means that all of my time, which is only 25 frames, is represented in each little chunk here. So as I scrub through, you can see a representation of each vertex scrubbing through its own time. When it gets to the end, the last frame, everything wraps back to the start. So in a game engine, really, what you're doing is sliding the texture. You're not sliding the actual UVs on that texture. You're sliding the texture relative to that UV set. That vertex can then get the data that's recorded into color. It can then apply a world offset based on that color data. So color data is stored in 3 channels. You have your red, your green, and your blue channels. And these are interpreted as X, Y, and Z. And we know each color can only be encoded as 0 to 1. We're encoding a pretty high quality texture here, but we aren't going into the HDR range. We're only encoding that regular 0 to 1 space in each color. So what do we do when our offset is greater than that range of 0 to 1? So this is where some shader work comes into play when you're decoding these to read them in your engine. So before I essentially bake the animation to a Vertex Animation Texture, my script runs through the entire cycle of animation, and it determines what the largest value is going to be in each one of those channels, and what the minimum value is for each one of those channels. So for the proxy, this means the largest value away from its original starting point. For the absolute world version, but you can think of its starting point as all verts are at 0. So what we end up with is an array of values of a minimum and maximum in each x, y, and z. Then when I encode it into color, I remap that range from the minimum x to the maximum x value to 0 to 1. So that's in the encoding process when I'm creating it. And then when we're decoding it, it's the same thing in reverse. So it's from 0 to 1 to your minimum and maximum values. When it's reading through this and determining animation, it's taking that color value from 0 to 1 and it's remapping it into the range of the minimum to maximum for that axis. So a little bit about the proxy versus the world approach. OpenVAT, my extension, by default uses the proxy offset method because it inherently allows for better quality vertex animation in most cases, because you should have smaller values of range. And what I mean by proxy is, if you take a look at this first example, the black dots are verts representing the proxy. And the white lines start at the proxy and end at the determined position as if it were decoded. So like we can take the top of the fin here, this is its proxy value, and then this is its encoded value at the frame that we're on right now. So the color data representing this is an X, Y, and Z translation from this value to this new value. And you can see the difference here in a world offset method where everything starts at 0, 0, 0, or the world origin, and everything's positioned relative to that. And there's actually a third version too that I didn't represent here because OpenVAT doesn't support it right now, so I have no way to demonstrate that. But it's called a delta time offset. If you could imagine this color of this first vertex being added with everything as it goes down through time, so that your resulting position is an aggregate of the accumulated time. And this is really useful for VFX simulations because you could have very small movement and very large movement at the same time without a loss of resolution, but it's a lot more taxing on the shader to decode it. So now I'm going to move over to this second example here. So what these are representing are the actual vertex colors that are driving the position. So if you can imagine, whatever verts are the same color in this map as they appear here, are those verts just being represented in 3D space and being represented in the texture they came in. So you'll notice if I scrub back to the beginning, this proxy encoded method is almost completely neutral colored on the first frame. It applied the deform from the armature, and then it knew that it needed to offset the additional deformation done by geometry nodes. So that's why you only see a little bit of color in this first frame. And as I scrub through, you can see as each vertex gets further away from its original position, you can see the largest difference in color change. In the world offset version, you see almost what you would imagine a world position map looking like. And on the very right, you can see the resulting version of each one of these. This wasn't a super complex simulation, so you don't see any kind of real difference between the two results. Unity and Unreal like to handle this sort of thing in different ways. So that's why I like an offset approach, because I know exactly where I'm coming from with the mesh. And if anything fails on the decoding process, at least it reverts to that original mesh shape. So I did note earlier that the y-axis represents time, but that's a little misleading because it doesn't necessarily need to represent time. It represents progression over the animation. And you can see this here. I put together a little demo of a proximity-driven vertex animation. So as I move this empty, these vertex animation textures of these little flowers get animated over their individual timelines based on their proximity. And this can be done in game engine shaders too. It takes a little more work to set up, and it takes a little more computing power to do, but there's a lot of different ways that you can control the animation of a vertex animation texture. You can even blend two together to control things like face shapes. You could combine skeletal animation with vertex animation textures to do things like clothing on a character that you don't want an active clothing simulation running on. And a lot of this is becoming more popular as more developers are trying to develop for augmented and virtual reality. There's a lot more hardware limitations on things like complex rigging. So a control method like this could be really useful for a lot of different situations in game. Even things like clothing simulations being tweaked by proximity to something or by additional values in a script. And I have a third demo to show kind of in this realm. I have this little scene of a lawnmower, and the grass is actually animated to sway in the wind. And this animation is driven by a vertex animation texture. But you'll notice I also have this big mask over on the left side. And if I paint on this mask, you can see it live updating what's actually being animated and what's not. So the low-cut grass is actually a frame of the texture that I purposely set the scale of all the blades of grass lower than all the other frames. And then I have a looping animation of the grass in the wind for all of the other frames. What this mask is lerping between is that one frame and the entire animation. So you could use this even to combine two vertex animation textures, blend between two for things like a character controller, or if I wanted the grass to sway different ways in different kinds of wind. And you could animate this blend dynamically too in an engine. If you have a way to draw a texture dynamically, you could do what I'm doing in scene here based on a character. We went over basically what vertex animation is, but how do you actually create this? For right now, we'll just work on a simple example of encoding. So to get the extension yourself, all you have to do is open Blender Preferences, go to the Get Extensions tab, and then search for OpenVAT. Once you do that, it should be enabled by default, but you can check if you go to the Add-ons tab and search for it again. And make sure the box is ticked here. And then what you should get in your 3D viewport is this tab that says OpenVAT, Vertex Animation Encoding. And it's a pretty simple panel that just gives you an output directory. This is where the textures and the final model will be exported to after running it. And then it just gives you a couple options here. We really only talked about position mapping. I allow you with this tool to also encode the normals. You might know if you've ever made something like ocean using a world position offset in Unreal Engine, that you have to pay attention to the normal handling so that your reflections act properly when you have the distortion for waves. It works the same way in vertex animation. You need that normal data to go along with the position data because you're essentially telling the shader new positions for every vertex, and it's still calculating reflections and lighting off of the original meshes data. There's two options here. You can throw that normal data into a separate map, or you can use it packed. And pack just means it's going to pack into the same texture as the position data. The only other options here are to use a custom proxy. I'm not going to get into that too much right now, but that has to do with the proxy encoding method. It just defaults to frame 1 of your animation regardless, but if you wanted a specific arrangement of vertices to start with as your proxy, you could use that custom proxy. And the way that works is if I had 2 objects in scene, the selected object would work as the proxy and the active object would work as what I'm actually encoding. And then the final option is just to perform cleanup, and that is, it goes through a process to encode the animation. And for most cases you should perform this cleanup, you should just keep that box ticked. But if for some reason you're having an issue with encoding, it's kind of like debugging if you turn it off. You can dive into the new scenes it creates and you can kind of troubleshoot what's going on. But let's just get into it. So I just have a cube here and it has some subdivisions so we can deform it. And I'm just going to throw a simple deform twist onto it. And I'm going to animate this twist over, I'll say 20 frames. And I'm not trying to make anything specific here, I'm just trying to show kind of the process of how this works and how it can stack through your modifiers. So with that in mind, I am going to add a geometry nodes modifier, and we're just going to add some scale over time. So we'll scale it on the x-axis. Now I'm going to set my start and end frames to 1 through the length of my animation. Right now this only works with the starting frame of 1. Something I wanted to add in an update for a while is a custom range to start with. But right now it just has to be set to 1. I'm going to make this loop just because I like when things loop seamlessly. And there we have it. This should be good enough for a demo of just showing how this works. For this demo, I'm not going to perform cleanup. I want to show you what happens kind of in the background. And I will include a packed normal map so we can see how that works too. And I'll just run this operator. So we'll see after that runs that now we have a new object in scene that's called cube VAT. And this does not have any of the same modifiers as the original. This is the original. You can see the simple deform and the geometry nodes. And this only has a geometry nodes modifier, which is our OpenVAT decoder. Now in Engine you would do this in shader, and with Eevee's new displacement in 4.4, I can probably do this in Eevee, but I haven't tried that yet. But this is simulating what an engine would do in a shader to decode. And I'll just run through this quickly. I'm not going to get super in the weeds with it because we already went over kind of how this works. So we're using our UV map that was created when I ran the operator. I'll actually show you the UV map here. You can see it arranged every vertex in order in rows that were appropriate for the size of the texture that it rendered. So it uses this UV set. It samples the image texture over that UV position to get color data. So what we're sampling here is color data per vertex based off of that grid. And then here you see the range remapping done per channel. So our red value is being remapped from 0 to 1 to our x min to our x max. And this was also set automatically for us when I ran the tool. OpenVAT also exports this data in the form of JSON that looks like this. We can see that we have 2 arrays of values. So these are our x, y, and z minimum values and our x, y, and z maximum values. This is so if you wanted to script something in Engine, you could easily do that. Just import your texture and then script the values to import into this, so you don't need to be setting that manually. So after our remap here, all we're doing is going into a simple set position node using the offset. Now it's critical I'm using the offset here because this is offset from the original vertex position. that's all there is. So really just sampling color, remapping that color into position data, uh, calculating the frame, and setting that final vertex position based off of the frame. I do want to show you what the output looked like for this. So on the top here, you can see this is our position data, but this is actually normal data. And this is encoded in the same way. This is for every vertex, its normal facing direction. And this is done in object space. So if you were using this in Engine, you could decode the position, and at the same time, you could sample this same texture to calculate the normal for that vertex and get accurate reflections. So let's go through what actually just happened with the encoding process there. OpenVAT makes two new scenes, one called a proxy scene and one with the label _VAT. The proxy scene just holds information about that proxy mesh so that we can calculate this. I'm not going to get super in the weeds with how this process actually occurs because it's pretty complicated, but I do want to give a quick overview. It uses geometry nodes to create these, which are the representations of the vertex position. So this is one object using geometry nodes, and this is a second object using geometry nodes. The difference between these being that this one has this box checked, which is telling it to use normals, and this one does not. And the script that ran in the background gathered all of this information for us and filled this out. So we know it's using the proxy that was in the proxy scene, our original object being the cube, the number of frames, the determined amount of wraps, so how many lines of vertices do we have, and then the x and y resolution to calculate how big is geometry to represent 1 pixel of this texture. And then you can see as I scrub through the frames, it's only displaying one set of vertices for each frame. Now it is displaying the normals as well as the object decoding, but one of the limitations of Blender's dependency graph, which is where this is encoded from, is that it can only evaluate 1 frame at a time. And through geometry nodes, we're getting the offset of each vertex from its proxy position, and we're representing that in that remapped color value. So we have geometry nodes to make the actual pixel size accurate, and it's returning a pixel offset, which is creating what creates that X value. We are wrapping it by time. We're defining colors from the proxy mesh here, and this is where the actual encoding mapping happens. You see we're going from our minimum and maximum values that are represented here into 0 and 1. Capturing and storing attributes for that color data to pass it to the material. Here we have another node group determining the actual position size relative to the scaled value of the resolution that it will be rendering. Here we have a calculation to determine those wrapped sections. And then this is calculating the Y offset to make sure that that's accurate every frame to be exactly 1 pixel. Then we finally have positioning and transform data to fit it accurately into where it needs to be for the camera to render it. This is a transform operation to be able to fit the normal map in with the position data on the same pack. And finally, we have our attributes that are being passed to the shader. And here we're capturing the attributes to be passed to the material. And if we look at the material, we can see it's really simple here. We just have toggle, which basically chooses between normal color data and regular position color data. And this is just a straight shader, so we're getting just that color position. We aren't passing it through any kind of shader. It's just an unlit representation of that color. First, it runs through some Python scripts to determine the values that will be used in this geometry node's modifier. It sets up that proxy scene, sets up this VAT scene, sets up the one or two geometries depending on what's needed here, sets the render resolution of the scene, and now since we can only display color data for one frame at a time, if we take a look at our compositing nodes, it sets up this compositing tree to basically render over itself for every frame. So it renders with transparency, and then it renders the next frame in the sequence, and it Z combines with itself. So then every frame is represented into what we've been looking at for the rest of this video. As far as I know, this is the only open source extension for creating Vertex animation that's available, and the only one I know of that can handle something like geometry node encoding. So it being open source, I'll link the GitHub in the description too. And I'm always interested in what anyone creates using this tool. Whether you had a cool idea to encode something or you got it working in an engine that I don't have supported right now, I love to see it all. So just send it my way. Like I said before, I am hoping to do more in-depth tutorials on OpenVAT itself and the decoding process, probably how to make those proximity-based shaders in Unity, how to make a decoding shader for Unreal. Let me know what you're interested in so I can prioritize those videos and have fun making some Vertex animation.